Okay, in this video, we're going to go over section 2.8, which is on one-to-one functions and invertible functions. So let me share my screen. This is section 2.8, one-to-one. We're going to talk about one-to-one functions and their inverses. So let's see, I don't know. I could just fit that. So the inverse of a function is basically, so again, functions are rules. You have a domain and a codomain. And the inverse of a function is that rule which undoes the function. So it's like the reverse or the opposite of rule of the function that you start with. And this, how you express this fact that it undoes it is through function composition. So if you have a function f, a function g, so if you have a function a to b, and you have a function b to a, then g is an inverse, and it'll turn out that there's only one inverse if it exists. So g is an inverse of f if they undo each other in the following sense. So the idea is that if you, so g has f and g are functions, they have rules associated to them. And the idea is that if you do the rule, if you apply g to x, if you just perform its rule, and then you perform the rule associated to f, you just get x back. You just undo it. And the same, and but it has to work both ways. The idea is that if you apply f to x, you apply the rule associated to f, and then you apply g to f of x, then it undoes it. It gives you back x. And a more concise way of saying this is that f compose g is the identity on function on b, and g compose f is the identity function on a. And this should sing. So this identity just means, identity function is just the function which sends an element to itself. So identity of, for example, identity of b sends x to x. And this all makes sense because f compose g is a function from b to b. So the domain and codomain are both b, and then g compose f is a function from a to a. So you have, given a set, you can look at the identity function on a set. And so, for example, it's given by this right here. And the same thing for a. The identity function on a is just that function which sends x to itself. It just maps the number to it. It doesn't do anything to a given element. So it will turn out, though, that not all functions are so-called invertible. So if this is all of the case, then you use this notation, f inverse. So g is called the inverse of f, and we use this notation, f negative, this negative 1. Now this doesn't mean like a multiplicative reciprocal. I should say not multiplicative reciprocal. It's just notation, shorthand notation, which reciprocal. I don't know if I spelled that right. Put that in question marks. No, I won't, because that might be confusing. But yeah, this might be spelled wrong. I don't. It doesn't really matter to me. This is not multiplication at all. It's just saying, it's just concise notation to express the fact that f has an inverse. So f -1, this is just the inverse of x, and we define it to be mean g. So g is the inverse of x, and we use this notation right here just to simplify things a little bit. And it expresses all of this right here. So all of this can be written as this. So you can write this. It can be rewritten. So it's like in some sense, so in one sense, function composition is like multiplication, but in another sense not. So it's like these two things cancel each other out to give the identity function. So the identity function is like the number 1 in multiplication. So you have 1. When you multiply, when you compose, so if you compose f compose identity of a, you get f back. And yeah, so if you compose a function with the identity, you get the function back. This serves same role as 1 in multiplication of numbers. So there is some analogy. Multiplication of numbers. Oops. So there is some analogy. There's some similarity. Well, this does not mean, so f inverse is not the same as 1 over f. But it's like it in a sense that the identity function is akin to the number 1 in multiplication. And that if you multiply 1 by any number, you get the number back. And if you multiply any function by the identity, you get the function back. And if a function has an inverse, if you quote unquote multiply or compose the inverse, you get the identity back. So it's similar to multiplication, but don't read too much into it. And namely, don't take f to the -1 power to mean this. This is not true. F to the -1 does not equal 1 over f. These are not always the same function. And so it turns out that not every function is invertible. That is, it does not have an inverse in the sense that I'm outlining here. It turns out, though, that all those functions which are so-called one-to-one are invertible. And so let's look at this class of function, these one-to-one functions. So I tend to use a different term for this. The book uses this, so I'm going to use these interchangeably. So these are called one-to-one or injective. And both, I guess, are sort of revealing. They kind of give you a sense of what one-to-one means, or what one-to-one or an injective function means. The idea is that given any 2 points in the domain of a function, those 2 points will never get mapped to the same function. So it's like it's one-to-one. That's maybe more telling, but injective in the sense that like you're injecting. So if you think of a function not just acting on points in the domain, but acting on the whole domain itself at once, it's like somehow fitting the domain inside the codomain without crushing or identifying any points. It's like embedding the domain into the codomain. So the setup is so let me just write down the definition. So we have a function from A to B. A is the domain, as usual, and B is the codomain. So a function from A to B is said to be, I'm going to just say injective, just because I don't feel like writing one-to-one. Injective, or one-to-one, if no two elements of A so no two elements in the domain have the same, whoops, image. And put a little bit more formally in mathematical symbols, that is, if you have x1 not equal to x2, and they are points in A, so x1 and x2 are in A and they're not equal, then f of x1 is not equal to f of x2. Now this condition right here is equivalent, so just using some logic, some notions from logic, if you have a statement P, just a little aside, P and Q are propositions or statements. Statements or propositions. Then the statement, the statement you form from them, the implication P implies Q, is equivalent to not Q implies not P. So in other words, you can like this if then, so this is, when I say P implies Q, I mean if P then Q. That I'm forming a new proposition from the propositions P and Q. And what this says is that this statement, this proposition, is equivalent to this one. That is, they have the same truth value. So right here, i.e. same truth value. So for example, if it is raining, I don't know, if it's if it is raining, then the ground is wet. That's equivalent to if the ground is not wet, so there's that not, then it is not raining, say. So something like that. I mean, you know, take that statement with a grain of salt. But the idea is that if you have the statement if P then Q is equivalent to if not Q then not P, and you can, you know, form examples to convince yourself of that. Like, yeah, I mean, I guess the only example that I can think of is if it's not rain, if it is raining, then the ground is wet. That statement is equivalent to if the ground is not wet, then it is not raining. So, but what all this right here means is that this statement right here, and I boxed out, is equivalent to maybe I'll put quotation marks, if f of x is equal to f of if f of x is equal to if f of x1 is equal to f of x2, then x1 is equal to x2. So this is just another way of thinking about injectivity. One way is if you take two distinct points in the domain, so two distinct points in the domain, then their images or their outputs have to be different also. Another way of thinking about is the following. If I take 2 points in the domain and I look at their images and they equal, then that means the 2 points had to be the same. So these are two different, or two equivalent ways, I should say. They, like at face value, they look different, but they're actually equivalent ways of looking at injectivity. So it's from this, it's easy to deduce the so-called horizontal line test. So we looked at another test, a similar test called the vertical line test. And that was about whether a graph of an equation corresponded to the graph of a function. And the idea is that if, so like for example, if you had this, and you drew this line that would intersect at 2 points, this meant that this plot does not correspond to the graph of an equation. So now we're going to look at a similar test called the horizontal line test. And this is a quick, easy consequence of the definition of injectivity. It's going to tell us another condition to determine injectivity. So with this more algebraic definition of injectivity, now we have this geometric definition of injectivity, or this geometric interpretation. So the test is that a function is injective, or one-to-one, if and only if, so this is important, we're saying that injectivity is equivalent to the following: no horizontal line intersects its graph more than once. And this makes sense. Let's look at a picture to see why this is the case. So it's going to turn out that the following is not injective, and we're going to want to see why from the perspective of, oops, I don't like this. From this more geometric perspective. Something's happening with OneNote. I'm not sure what. Okay. So suppose we have something like this. Something like this. So this is f of the function is the function we're going to call f, and it's a function from R to R. Now, the claim is that this is not injective. So if I just draw horizontal line, it actually passes through 3 points, right? This horizontal line. Let's call this x0, x1, and then this is x2. I don't really care about this point right here, because these 2 points themselves already show that this function cannot be injective. Why? Well, if you look at these points on the x-axis, this is the domain right here, the x-axis. Those clearly are not the same point. But if you look at their output, if you look at the y-coordinate of their output, they are the same. They're at the same height, right? Now, they're not the same point in the coordinate plane, but they are the same point along the y-axis. So that's why injectivity fails, because we don't care about the point in the plane per se, but we care about how far it is along the y-axis. So this shows that these 2 points, although they're different points in the domain, so the domain is the x-axis, and the codomain is the y-axis. So the outputs, their images, are the same. So this hopefully illustrates why. So in other words, for a function not to be injective, let's go back to the definition. Why is this not injective? So we have this horizontal line test, which supposedly gives us another equivalent condition for determining whether a function is injective or not. But let's look at why it's not injective from the definition of injectivity. So for a function not to be injective, we just got to negate the definition. In other words, we got to say, okay, we need to find 2 points for to break injectivity, to show something is not injective, we need to find 2 points that are the same, yet their outputs are not the same. I mean, their outputs are the same, I'm sorry. And we did that already. We found x0 and x1. And then we looked at, so this is f of x, this height right here. This height right here is f of x1, but it's also f of x, or this is f of x0, and this is also f of x1, but they're at the same height, so they're equal. So these points are not equal, but their outputs are the same, so therefore it's not injective. So hopefully this kind of illustrates why this horizontal line test is equivalent to injectivity. Okay, so let's look at an example. So this is example 1. So we want to determine whether this is injective. Is this injective? So there's a couple ways we could do this. What we could do is we could do this more algebraically. We could say, suppose. So remember what we need to show. To show injectivity, we need to say, okay, if we need to take 2 points, and we got to suppose that their images are the same. What we want to, and we want to show x0 is equal to x1. This will show that the function is injective. We need to establish that. We want to show that if this is the case, then it implies that this is the case. That is, if the images are the same, it implies that the 2 points are the same. Well, this equation is the same as x0 cubed and x1 cubed. Now, with odd powers, I can take the root, and I don't have to worry about pluses or minuses. So I can take the cube root of both sides. And because I'm taking the cube root of something cubed, the power will cancel out and the cube root will cancel out. And it will imply that x1 is equal to x0 is equal to x1. And then that shows, so it's a check mark, and that shows f is injective. We could do things, and this is the rigorous way. This is the more logical, precise way of showing injectivity. This is when you get into more advanced mathematics, this is what the mathematician is looking for, a proof like this. For our class, we can also, for purposes of our class, we can do things through a picture, but that isn't to diminish the importance of pictures in when you get to more modern mathematics, because pictures are meant to suggest things. They aren't going to prove things, but they're going to suggest something to us that might lead us to prove things. So pictures in general are not proofs. Pictures will not prove things, or you can't prove mathematical statements by drawing a picture. It's not rigorous enough, according to mathematicians or logicians. But they can sometimes inform us, like maybe we don't know whether a given statement is true, so we need to draw some pictures to determine whether it's true. Like maybe this proof right here didn't immediately come to us. We're like, okay, I don't know if this function is injective. Let me draw a picture. Okay, well, it turns out if you plot this function, it's going to look something like this. And you can find this out by just plotting some points or plugging into Wolfram Alpha. You can do one or the other. I suggest doing both. And it looks like it's pretty clear from this. If I just draw any horizontal line, it's going to intersect at most one point. So what, now this isn't a proof because it's impossible, because what the horizontal line test says, I have to consider every single horizontal line test, or every single horizontal line through the graph, but there are an infinite number of horizontal lines. How do I know that there isn't, you know, I've only done these few right here, but how, if I go further down the graph, all the way down towards infinity, how do I know that there isn't a horizontal line that intersects at 2 points and showing that it's not injective? I don't know. But this picture does suggest it looks reasonable that this function, it seems reasonable that this function is in fact injective. So I need to think about how would I prove that this is injective? Well, here's this proof. And as I said, it might not be immediately clear, or this proof might not immediately present itself to you, but at least the picture suggests that there perhaps is a proof that is an injective, and this is the proof. So I don't want to diminish the importance of pictures and drawings and thinking about things geometrically, but I just want to point out that they don't prove propositions. They don't prove, for example, that this is injective, but it suggests that it could be injective. So that's the purpose of pictures. So that's an example of proving something is injective. Let's look at proving something is not injective. So we have this function. Hold on, I need to stop sharing for a second. Okay, so let's get back into this example. So the example is g of x equals x squared, and we're thinking about g as a function from R to R, the real numbers to the real numbers. And we want to know is, we want to ask, or we want to determine whether this function is injective. So is this injective? Well, again, maybe it's not clear to us how to prove it one way or the other, but we can appeal to a picture. We can appeal to our geometric intuition to determine whether it is one-to-one. So if you recall, the graph of x squared looks like this. So it opens up on this side, and it opens up on this side. And from the picture, it should be clear that it's not injective. If you draw, for example, this horizontal line, it intersects, or at least it appears to intersect at these 2 points. Now, again, this isn't a proof, but it suggests, okay, maybe it's not injective, which means that there should be, I should be able to find 2 different points such that when I plug them in, I get the same output, I get the same image. And that, it's actually very easy to find such points. We can find lots of them. So suppose x, or take x0 to be -1 and then x1 to be 1. So these are clearly not the same points. These are clearly not the same points, but when I plug them into the function, I get the same output. So this implies that, oh, I'm sorry, these are all, let me just change this up. These are should be g's, but I'll just change it up here. So let's just take it to be f. Function is f. So this shows that the function f is not injective. And these functions, injective functions, are very important. So as I said, modern mathematics is really just sets and functions. And when you get into more advanced mathematics, you'll study things like group theory and topology, and injective functions are very important. They'll come in the injection functions, for example, in group theory will come in what are known as isomorphisms. And group theory is like basically, I mean, we're thinking about groups already. R with addition is a group. A group is just a set with some operation on it, so like addition or multiplication, such that you have things like associative law in that the function, the group has an identity element. In the case of this, 0 is identity element. Oops. So real numbers with addition, 0 plays the identity because when you add 0 to any number, you get the number back. And then you have inverses. And in the case of real numbers with addition, inverses are just negatives of numbers. And it turns out that you can talk about things like homomorphisms between groups. And homomorphisms measure whether two groups are the same. They're just different in different forms. Like, for example, if you take the integers, so negative, all negative integers or negative numbers like -3, -2, -1 up to infinity, and then positive numbers 1, 2, and 3 up to infinity with addition. This forms a group. But then you can also look at matrices. So a set of all matrices of this form. So 2 by 2 matrix where you have ones on the diagonal, 0 on the off diagonal, and n on the other diagonal with matrix multiplication, which I defined in another video. But I mean, don't worry about these details a whole lot. I just want to point out why injective functions matter. So this set of matrices forms a group. It turns out that this, say we'll call this G for group. It turns out that Z with addition and G with multiplication are isomorphic. They're the same group. And you're like, what? They don't look the same at all. Well, let's multiply two elements in here. So I take an element of this form, and then let me see if I'm not screwing this up. I take another element and let's multiply them. And you're going to see it looks a lot like just adding integers. So to multiply this, I do 1 times 1 plus n times 0. So that means I just get 1 on the diagonal. And then I do 1 times m plus n times 1. And then 0 times 1, which gives me 0. And then 1 times 0 gives me 0 here. And then 0 times m plus 1 times 1. So I just get 1 on the diagonal. And notice, like this, all you really care about in this matrix is this element here. So it's like when you multiply these matrices, it's like just all you're doing is adding these entries right here. So the isomorphism is not hard. So I can actually tell you the isomorphism is this. I take an integer and I map it to this. And you can prove that this is an injective function that preserves what we call the group structure. So integers with addition is a group and it has a structure. These matrices with multiplication is a group with structure. And it turns out this is an injective function, what you call an isomorphism in group theory. So these are, so at first sight, you might be thinking like, how are these even remotely the same? How is Z even remotely the same as G, this other group? It turns out they are identical in the sense that there's this injective function from them preserving the structure. So this is just a little aside. You don't have to worry about this at all. Group theory is something you take in maybe your 3rd or 4th year. and then you study more deeply in grad school. If you go for grad school in mathematics, sometimes even computer scientists take group theory. But I just wanted to show you the importance of these injective functions. So if you're interested in more of this, I certainly would. We can talk about this, but it's not. I'm not going to test you on this at all. So, so let's get back to the example. So we proved is that this is so when you take so I'm kind of using F all over the place. I'm using F differently now. F means something else now. In fact, let me just get rid of this notation. We kind of use in group theory, we tend to use phi. So I'll just use that. So that's the isomorphism between these two groups. And if you're interested in group theory, we can talk about it some more. It's a pretty fascinating area of mathematics. So back to the example at hand. So we have a function from R to R, and the function is f of x is equal to x squared. And we just determined that it's not injective. But what if I change its domain? So what if I change the domain and I just redefine it and I ask whether this is injective? It turns out that this is an injective function, and we can see that geometrically. Because when you restrict the domain to just the positive or non-negative numbers, you just get this guy here. It's like half of the parabola. And of course, from this picture, it's clear that if you draw any horizontal line, you're going to only intersect at one spot. But you can prove this rigorously. You can say, okay, suppose you have 2 points, x1 and x2, in here. So there's some non-negative number with this. Well, remember what the goal is. We want to show, so if their images are equal, we want to show that x1 is actually equal to x2. Well, this right here means x1 squared is equal to x2 squared. Now, in this case, I'm going to take the square root of both sides. So if I take the square root of both sides, I have these plus and minuses, but we know that we can't have negatives because remember we started with x1 and x2 being positive, so have to get rid of, have to ignore negative roots because neither number is negative. So that means they're just both positive, right? But if they're both positive, then they just have to be the same, right? Because this says plus or minus x1 equals plus or minus x2, but I'm just going to ignore those negatives. So if I just ignore the negatives, I have pluses, and I can, of course, just drop the plus signs, and that will just mean that x1 equals x2. So that implies that f, when you restrict the domain in this way, is injective. So up here, we have restricted the domain. So we're thinking about x, but with the domain restricted. Now, it's not always the case that you can restrict the domain in a nice way to get an injective function, but sometimes you can. But the point of this example is that you can't just look at the rule of the function to determine whether it's injective. You have to look at its domain also. You have to be careful about the domain. So with all of this in mind, we can now define the inverse of a function. So let's look at the inverse of a function. So let me introduce this definition. So we're starting with a f as a function from a to b is injective, so we need injectivity from the start. If it's not injective, then this definition won't make sense. Then its inverse function, which we denote as f to the negative 1 power, and it's a function from a to b, is defined by the following. It says that f inverse of y is equal to x if and only if f of x is equal to y. And this is for any y inside B. So what this says is, if you want to look at where a given, or if you want to look at how f inverse maps a given element, so you want to look at where it sends, if you want to look at where f inverse of y sends, or if you want to look at where f inverse sends y, you need to go back to the original function, find the value of x that f maps to y, and that will be the output of f inverse. And it's pretty clear that if you compose these two functions, then they're just going to undo each other. So why is that the case? So remember, suppose that this holds right here. This is as equivalent to that being true. Well, y is equal to f of x, so I can substitute y into here. And then I can do the same thing, switching f inverse and y inverse. So I can say, we know that if this is true, then x is equal to this, and I can substitute x into here, and I get this. So they undo each other, as we said they would do, as they said we would in the beginning. So let's look at an example. So this is example 4 in the book. So we suppose that we have the following. We have a function, we don't know what it is, but it sends 1 to 5. It sends 3 to 8. And it sends 8 to negative 10. We want to find f inverse of 5, f inverse of 7, and f inverse of negative 10. Well, let's go back to the definition of inverse function. Let's just look at this one for now. So we want to determine what its output is. We don't know what it is, so we'll just call it x. Well, remember, f of, say, y, so y in our case is 5, f inverse of y is equal to x, if and only if f of x is equal to y. So this is the case if and only if f of x is equal to 5. Well, so we need to find that x that gets mapped to 5. Well, we're given that f of 1 is equal to 5. So that implies that x has to be 1. Remember, these are injective functions. So this is the only value of x that can be mapped to 5. There can't be 2 different ones, because then that will contradict the fact that we're dealing with injective functions. And then we do the same for the other one. I'll just do one more, and I'll leave the other one for you to do. So we don't know what f inverse of 7 is, so we'll just call it x. But this is the case if and only if f of x is equal to 7. So again, we have to look, wait, something doesn't seem right. I see. So this is not right here. This is supposed to be f of 3 is equal to 7. So f inverse of 7 equals x, x being which where x is to be determined, if and only if f of x is equal to 7. And if we just go back to what's given, we're given that f of 3 is equal to 7. So this implies that x has to be 3. Can't be anything else. And then you can play the same game for the last one, f of inverse of negative 10. So now that we've done this example, let's look at another type of example of verifying that two functions are inverses. So let me just write this down. We have this, I've already pointed this out a few times, but we'll just write it down because the book points it out. So this is the so-called inverse function property. It gives us another way of determining the inverse. So we have some function f, and it's injective. So let f from a to b be injective. Then the inverse function f inverse f to negative 1 satisfies the following cancellation properties. We have f inverse of x, f of x is equal to x for all x in A, and f inverse of x is equal to x for all x in B. And then conversely, any function satisfying these equations or these cancellation properties is the inverse of f. So let's look at an example where we do this. We verify these cancellation properties hold. So we have f of x is equal to x cubed, and g of x is equal to x to the 1/3 power. And we're thinking about both of these. So f and g are both from functions from the real numbers to the real numbers. So I'm just using this shorthand. So we're saying f comma g just means that they're both functions from R to R. And we want to verify that they're inverses of each other using this cancellation property. Well, it's pretty straightforward. We just compose the functions f of g of x, and so when we plug in g, we get this. And now we're going to plug in x to the 1/3 into f. So that means we have to write this down. And then 1/3 and the 3 cancel, and you just get x back. And I won't do the other one because it's similar. But you can check that if you compose, if you compute g of f of x, you'll also get x. So now it's not always the case, or it's not always obvious that a function, it might be obvious that a function has an inverse, but it might not be obvious what that inverse is. So we have a way to find the inverse of a function. And basically the idea is, I'll just write the steps down. So finding the inverse of an injective function. So the first step is you write function as y is equal to f of x. Solve for x in terms of y. And then the last step is interchange x and y. And then this will give you the inverse. And the idea is basically comes from the fact that, again, that from the definition, y is equal to f of x if and only if f inverse of y is equal to x. So if you have this equation right here, you can solve for it in terms of x. And when you do that, you'll get something like this, and then this will kind of tell you what the inverse is. But you just got to follow these 3 steps. So let's look at an example of this. So this is example 8. So we have f of x is equal to x to the 5th over minus 3 to the divided by 2. And so we're going to set y equal to this function, and then we're going to solve for x. So I'm going to multiply both sides by 2 to get this, and then I'm going to add 3 to both sides to get this. And then I'm going to take the 5th root of both sides, and then I'll get the following. And so when you switch things back, interchange x and y, you get the inverse. So f inverse of x is equal to 2x plus 3 to the 1/5. And I won't go through it, but if you actually compose f of x and f inverse of x both ways, those 2 different ways, you'll get x, you'll get the identity function. But I won't go through that. And the last thing I want to talk about in this video is the graph of an inverse function. So this idea of interchanging has a geometric interpretation to it. So again, if we have that f of a is equal to b, suppose we have some function f and it's invertible. This is the case if and only if f inverse of b is equal to a. And what this means geometrically is that a comma b is a point on the graph of f if and only if b comma a is a point on the graph of F inverse. So if you draw, so this has the interpretation that when you start with the graph of F, you're reflecting it about the line y is equal to x. So this looks something like the following. So you have this line. I'm trying my best to draw it straight. And if you have a point over here, suppose that's a point on the graph. A comma B. This is kind of small. Then so you go over A units and go up A units, or up B units. The opposite point is that you go up A units, I don't know, there maybe, and then over B units, something like that. It's not a perfect drawing. Over B units, you get somewhere like right here, maybe right here. I don't think I went over enough for A, B. So this will be point B comma A. This distance is supposed to be the same as this distance, and then this distance is supposed to be the same as this distance right here. But they're kind of, it's not perfect. I'll pull up Wolfram alpha. There are reflections about this line y is equal to x. So let me pull up Wolfram alpha. And let me see. So Wolfram alpha, which I definitely promote the usage of. So let's look at, we're going to plot square root of x minus 2. Now I'm not going to go through it, but you can, it turns out, now again, you have to worry about the domain. Actually, let me plot, so I'm going to plot this function, then I'm going to plot y is equal to x. And if you go through the work, you can show that the following is the inverse of it, a square root of x. Square root of x minus 2. It's x squared plus 2. But you got to be careful about the domain. So we'll say from 0 to infinity. Because they won't, you know, x squared, anything squared is like a parabola. So you have this parabola shape right here. This is not really showing what I want. Wolfram alpha is not cooperating. Let's see, from it's not zooming in the way I want it to zoom in. Let's maybe do on a smaller scale, 2 to 10. Nope. It's too big, I guess. This is unfortunate. All right, well, actually, you know, I'm being a dummy. This example's in the book. You should be able to fiddle around with Wolfram alpha to get the plot work. I'm not sure why. Let me just try one more. Yeah, I don't know why this is not working, but I already did these numbers. Maybe just 2 to 3. Yeah, it's not coming out, but that's all right. So Wolfram math is not perfect, but it is helpful in a lot of ways. So let me just pull up the book. So this is basically the example I was going through here. So you have this function right here, and they show you how to find the inverse. It's pretty straightforward. I'm not going to go through that, but I just wanted to point out that if you can properly plot these graphs, the graphs of these functions, you can see that there is a symmetry about this line y is equal to x. So you basically flipping it over, the line y is equal to x, which is the identity function. And here's another plot. Here's what I was trying to draw. So you have this point AB. If AB is a point on the graph, then BA is a point on the inverse of the graph, or the graph of the inverse, I should say. And they're kind of symmetrical about this line. You're just rotating them about it. And here's some more examples of plots. So this is a little bit more abstract, and we had a kind of tangent, went off on a tangent on group theory. Hopefully that was interesting to some, at least. And it should be, because I mean, this group theory really connects with modern fundamental physics and things like that. So it has some deep connections to science and physics in particular. So yeah, don't worry about a lot about that, but just worry about the injective functions on real numbers. That's what's mostly important. So I'm going to stop now. That's enough for today.